today. This informal body count of the room is just a tad over 40, which is a whole new low. I don't know what to do exactly. I mean, I appreciate you guys being here, and I encourage you to keep coming, but it's starting to feel a little sparse and a little lonely for me up here, so I don't know. I don't know what the solution is. I think people are taking a little bit too much advantage over the fact that I post these recordings as a fail-safe, so in case you're sick or something like that, that is exactly what they're doing. They're sick every day, and that's really not cool with me. So if things don't change soon, then I'll probably stop posting the recordings. It won't affect your life, but anyone who's listening to me right now on the recording, it will affect yours. Okay, so please start coming to class. It's better for everyone. Okay, coupon collector. Got a couple problems that are going to be applications of the expected value stuff that we've been doing, and then we'll introduce a new concept called variance. Many of you have seen something like variance, maybe standard deviation, maybe variance, one of the two. Anyway, we're going to introduce that today. Okay, so coupon collector. Here's the situation, and we've all experienced a contest like this, be it Starbucks sort of thing with the coffee that's actually up here, or a McDonald's sort of like a Monopoly thing where you have to collect a set of 3 or 4, 4 railroads or something like that. And if you do, you get a prize. Anyways, so this one attacks a general problem. Okay, so it asks you how many times do you have to buy coffee or buy a meal or McDonald's or whatever before you're expected to collect all n colors. Okay, so we're going to analyze this, and we actually have all the tools that we need to analyze this problem, believe it or not. And first, I want you to consider, a sequence of coupons that you get one at a time. Maybe this is a little bit sad off the bat to get a whole bunch of red all in a row, but yeah, so this is time goes from left to right here. And, you're happy, though. You're happy every time you receive a new colored coupon, right? You're really happy. Okay, so we sort of consider, this is an incremental process where every time you get a new color, that's a good thing, and you're +1 to the good. All right, so if you look at the, here, of course, you get one coupon. You always get a unique coupon on the first go. Second go, you get red. But on the third go, you get red again, so it's not until the second trial there that you get blue, and then you get red again. You're sad, but you get pink. That's new. And then this one takes a little while. You get red, and then you get blue, and then you get tan. Gray is back here, blue and pink. Okay, so cyan. Okay, so the time in between is going to get longer and longer the more colors you collect, the more unique coupons you collect, but you will eventually trip over the ones that you need. Okay, so this segment, I guess, continues over here. You already have pink. Okay, so this is the idea of breaking this problem into segments. Okay, so you divide things into segments, where segment I, and we could maybe call this like S sub I. S sub I ends when you're happy, okay, when you add another color to your bucket. Okay, so here's like segment 1, this is segment 2, ends after 1, segment 3 takes a little longer, okay, segment 5, segment 6, you've collected 6 colors then, segment 7, will end somewhere down the line. Okay, and by breaking up the problem into these pieces, it's going to be more manageable. Okay, and we're going to take the sum of all those segments. That's how long it's going to take for you to accumulate everything. Okay, so the sum of all the segments, each segment is going to have a length of x sub k, and we're going to add them all up to find the length c being all the coupons that you collected. Okay, so I guess I have it on the next slide here. Okay, so C is the total length of this process, the total number of coupons you collect. It's going to be x1 plus x2 all the way up through xn. And our goal here is to find E at C. Okay, this is, immediate. We've been talking about linearity. Linearity will immediately chunk this into pieces where all we have to do is find the expected value of each of the individual pieces and add them up. Okay, so that is a nice consequence. So the expected value of C is really the expected value of this entire thing, but by linearity, it's going to be the expected value of x1 plus the expected value of x2 plus, and so on, the expected value of xn. Okay, so again, linearity means we only have to pay attention to a small piece of this problem rather than the entire thing holistically. Okay, we still have to pay attention though. We still have to figure out what the expected value of x sub k is. Well, let's think about it for a sec. If you're in segment K, it means that you already have collected, I guess, K minus 1 colors so far, right? Segment 1, you've collected 0. That makes sense, yeah. So after, K minus 1 colors, you'll be in segment K. And you keep on plucking out coupons, right? One at a time. And it's possible that you fail, and then you have to redraw, or it's possible that you succeed, and then that ends segment K. This should sound like a distribution to you in your head. What distribution is it? Geometric, yeah. You keep on trying things over and over and over until you succeed, and then you quit. And we're interested in how long does it take until you quit. It's exactly a geometric distribution. Okay, so let's get that down. Okay, so if you're in segment K, then you've seen K minus 1 coupons so far. The probability of finding a color you haven't seen, so we'll call it a new color, on your next coffee, is, well, let's think about this for a little bit. There are certainly n colors, right? So it's going to be something over n. Initially, it's going to be, if it's segment 1, it's going to be n over n, right? You automatically get a new color. You automatically win. As you go down, right, as k increases, it's going to go down by 1, and 1, 1, 1, 1, 1, right? So your next time will be n minus 1 over n, n minus 2 over n. Okay, so we're really going to subtract something here that should increase as k goes up, but it should give you 0 on when k is equal to 1. So it'll be n minus k minus 1 over n. And the segment ends when you succeed. Thus, it's a geometric distribution. Okay, so x sub k is geometric at this probability, so n minus k minus 1 over n. Now, our goal here, of course, is to compute the expected value. Remember what the expected value of a geometric is? What is it? Yeah, 1 over p. Yeah, 1 over p. And p is this, right? Okay, so maybe we'll just continue the sentence here. So the expected value of x sub k is 1 over this. So we just invert that fraction. So n over n minus k minus 1. Okay. All right, let's plug it in. Okay, so E of C is going to be this for each k from 1 through n. So we'll just wrap that up into a sum. So k is equal to 1 up to 1 to n of n over n minus k minus 1. And the denominator is the thing that's changing. Okay, the numerator is actually something we can factor out, so we'll just pull that out. But the denominator is the thing that's changing. And if we look at what happens when k is equal to 1, that'd be 1 over n. K equals 2 will be 1 over n minus 1, and then 1 over n minus 2, and so on. Okay, so this is going to be 1 over n plus 1 over n minus 1 plus eventually a half plus 1. And again, we have this harmonic number thing going on. Some of you ask me, like, why is the harmonic number, follow the natural? I'm going to show you this over here for you right now. If you look at just what's going on with this bit here, a half plus a third plus a quarter plus what, this is what the graph looks like. It's not quite to scale because it's hard to see under that thing, right? It gets really, really packed. But you can find the area of this, right? There's, you put a bar, another bar, another bar, and it's bounded above by this curve. This is 1 over x between, I don't know if this is n over here, right? That's 1. It's going to be the integral between 1 and n. Okay, so if you were to just take what's over here, a half plus a third plus a quarter plus an nth, okay, this is going to be bounded above, and it's very easy to see, the integral, there's only these triangles to add up, or they're not exactly triangles, but anyway, it's not going to be very far off of this, 1 over x dx. Likewise, you can do the other bound. Okay, so this is another way of bounding the sum by doing, the other rectangles. Okay, so that bar, if we extended that upwards, right, that would be a bar that has an area of 1. This would have a bar area of a half, a third, a quarter, a fifth, a sixth, a seventh. Okay, so likewise, you can say that that area, the sum of those rectangles, is bounded below by the same or a similar integral. Okay, so what integral is it? Okay, so it'd be 1 plus a half plus a third, okay, plus 1 over n minus 1. That is bounded below by the same integral. Okay, and this integral trick is, it's not something I'm showing you lightly. This is a thing that's used to approximate discrete sums, not just in this course, but courses that come down the line. I also teach Compute 307, and we use this trick to get around some interesting sums to solve for big O in places where you can't find an analytical solution. It's kind of cool. And all you need is less than or equal to for big O. Well, here, we're not going to get an exact answer. I mean, we can certainly write a computer program that will do it. But we're kind of interested in, what's the running time? How many coupons do we have to collect, in general case? So this thing will, let's just do this. We'll do the integral from 1 to n of 1 over x dx. Okay, so it's certainly bounded above, the expected value is certainly bounded above by this, which we know to be the natural log of x. And of course, the natural log of, when we evaluate this, the natural log of 1 is 0. Okay, so this is n times the natural log of n plus 1. Okay, so this thing, this amount of coupons we expect to get is, you know, it grows like n log n. So we expect to buy big O of n log n coffees to collect n colors. Cool? Yeah, love this problem. Okay, any questions about this or the analysis of this problem? Yeah? Is it good? Okay, we're going to do one more problem, and this is actually a computing application. Okay, so, and it's a routine that you write in your first year computer science course. I guarantee everyone wrote a routine like this, and you probably keep writing routines like this as, you know, parts of larger programs going forward. Okay, and it's the max routine. Okay, so a typical routine to find a max of a list of n values, I guess, is first you initialize the value max to be minus infinity, or something that if this thing was empty, that would obey the, it's like the identity element, so it would obey the identity equation. And then you scan through, and you keep on updating the max every time you trip over a new global max for what you've seen so far. Okay, so you do that with an if statement. If AI is bigger than the max so far, you update it. But there might be some expense to doing that. Okay, so we all know that this thing runs in order n time, right? We all know that. But how many times does this line run? Okay, so how many times do you update the max? And this can be relevant if you're updating the max on some, you know, largish database as a live quantity. Okay, and it's expensive to maybe update like a web page, you know, something that's out there, and, you know, not local to the computer, like out there on the internet where things tend to be expensive. Okay, so treat this line as an expensive line. Like it might cost you several seconds to, you know, send the remote procedure call up to cyberspace. Other people have phrased this problem to me in another way, because you often maximize various quantities in your life, right? For example, it might be an expensive operation if you were trying to hire somebody, say an assistant, like a personal assistant, and you just don't know exactly who's out there, right? You don't know who's out there. So the first person you hire them, and then you might meet somebody that's better, right? You want to hire them, sure. So you hire them and you replace the person, but it's expensive to replace people, right? It's expensive to fire people. So you might encounter this as a real life expense. Okay, that's not really the problem that everyone tells me about. They talk to me about getting divorced and remarried, so maybe it's a little less savory to talk about that. But anyway, you can treat this sort of updating to the maximum. You know, we all want to find the best thing that we possibly can, the best person for whatever task we want. That line, that operation can be expensive, both in computer terms and in real life. Anyway, Let's talk about this computer program that you probably haven't really thought about. Okay, how many times does that line get run on average? Well, we can, from computer science like 101, we just, discuss the best case and the worst case, usually the worst case. I mean, the best case is it's never really updated more than once, right? You find the max right away, it's updated once, and life is good. Okay, but it's possible that it's really bad. And it all depends on the order of the array. Okay, and assuming they're all distinct elements, what is the worst case? N times. Why? Or how? Good. Yeah, so if it's in sorted order, if it's in ascending order, then it gets updated every single time, right? Every single time you do another check. Okay, so ascending order. This line gets run n times. Now, the best case order would be one time, and presumably we can have anything that's in between. And when we ask ourselves, what's the average case? Well, in computer science, we need to make assumptions in order for us to proceed, because, the ordering of A might be pre-processed in some way, and it might be that ascending is a very common order. I mean, that's typically how we like to read arrays. But that's kind of hard to, do a distributional calculation over, right? It's hard to do expected value for that. Okay, so typically what we do in computer science is assume that all possible things are equally likely, uniform distribution. Okay, so we assume all n factorial possible permutations are equally likely. Do we know what the n numbers are? No, we don't have to. We just have to know that they're all different. And you can imagine, instead of you having numbers, you just have rank orders. So there's going to be one number that has rank 1, one number that has rank 2, 3, 4, n. And that's all you need to know. That there's exactly one of each. Yeah. So just imagine they're 1 through n. Okay, so let's run this routine n times, I guess. And on the kth iteration, we're going to let x sub k be the indicator variable that this thing is run on iteration k. And we'll let x be x1 plus x2 plus all the way up to xn. And I have to go to another sheet of paper now. And we want to find expected value of x. And as usual, the expected value of x is going to be the expected value of x1 plus the expected value of x2. Okay, so linearity has been our friend throughout all these things. Okay, so all we have to do is find the expected value of x sub k. Okay, first of all, this is a Bernoulli distribution, right? It's an indicator variable. What's the expected value of an indicator? Nope, not NP. Say it again? No, it's not a half. I mean, it's a half if it's 50-50 for it to be a 1 or a 0, but it's not a half, no, sorry. It's P, yeah. So the probability that that statement gets run is the expected value. Okay, so all we have to do is figure out the probability that star is run on loop K. Okay, so let's think about it for a sec. On the kth loop, you're basically looking at the items, A1 through K, right? A1 through K, so there's K items. And there are K factorial possible orderings, right? That's a lot. But you only update the maximum in some of those, right? When are the ones that you update the maximum on the kth iteration? If the kth number is K, yeah. Okay, or if the kth number is the biggest one you've seen so far, right? So all of those have a certain, rank order to them. If the one that you come across there is the one, then you're good, right? And that happens more or less one chance in K, right? It has to be fixed in its last position. All the other ones can come in whatever order they wanted before, and maybe you cared on earlier iterations what that ordering was, but you don't care anymore. Okay, so there's K minus 1 factorial of those. You can divide by K factorial, you get 1 over K. That's another way of looking at it. Okay, so the only way that you run that is if the ordering that you have of those K elements has the max of those K elements right where you are right then. Okay, and that's a 1 in K chance. Okay, so for star to run on loop K, A of K must be the max of the first K elements, and that's a 1 in K chance. Okay. Or you can take all the permutations, K factorial of them, and there's K minus 1 factorial of them that have a specific element in the very last, and you just divide them, and everything divides out except K. Okay, so either way, 1 over K for each of these. Okay, so the expected value is, I guess, 1 over 1, so that's 1 plus a half plus 1 over n. And again, we get the harmonic numbers, right? So it's the nth harmonic number, which is approximately the natural log of n. Okay, so in terms of running time for updating this, web page or updating, whatever it is that's expensive, that expensive operation is run log n times, even though the algorithm is order n in the worst case. Cool? Yeah, pretty cool. Okay, questions about this? Is it good? Alrighty. Yep. Sorry? H sub n. H sub n. Yeah, sorry, my handwriting's not best sometimes when I'm rushing there. Yeah. Okay, good. All right, time for a summary. It's a rather dull-looking slide, but anyway, we have looked at expected value, where the distribution is centered for all the distributions that we tend to care about. Okay, binary thing, Bernoulli or indicator, it's tied to the probability of the event occurring. Uniform is more of a classic type of average. You add up all the values and divide by n, so it's just weighted equally. Geometric and binomial, maybe it's surprising that these things are so clean, but geometric 1 over p, okay, so you just invert it. Binomial, it's the sum of a whole bunch of Bernoullis, so np, that's a good way of thinking about it. And we did Poisson as well, okay, and this lambda, remember, is the average number of balls per bin, so that average turns out to be the average over here, which is good. It's sort of follows our intuition. Okay, time for us to introduce something else. Okay, so we talk about spread. That's the sort of other main metric that we use to analyze distributions. And where it's centered is usually not enough. Okay, and for an example below, so this is a Gaussian curve. We don't do a lot of Gaussians here, but it's a very classic. It's actually an optimized bell curve. It has some nice properties that were discovered before statistics was actually a thing. Anyway, so it's a bell curve. And, you know, anyway, the way that we talk about bell curves is we sort of talk about how many, how wide it is and how far away you can get from the center without it being unlikely. You talk about, like, you've heard of, like, standard deviations away from the mean, right? Standard deviations away from the mean. So, it's like 1 sigma or 2 sigma event is pretty likely. If you're 3 sigmas or more above average, that's really exceptional. Like you're really smart, for example, or really athletic, or whatever talent that you have. You're way, way, way above average. Sorry, you got a hand up, yeah. Mm-hmm. Yeah, so this is, the Gaussian distribution is continuous. And so I might say a few words about that at the end of the course. But the binomial is basically like, its limiting case will approximate this. Yeah. I have a computer demo that it's pretty cool, actually. It shows that everything kind of eventually becomes a Gaussian if you if you roll enough dice. Yeah, it's pretty cool. Anyway, to talk about spread, let's look at the following 3 random variables, okay? So one of them has a probability of x being 0 is 1, okay? So with 100% chance you get a 0, okay? That's not very exciting. What if you had plus or minus 1 with probability of a half? Well, the average would be 0 still, right? And same thing for plus or minus 1,000 for z. With a probability of half. Again, the average is 0, but these things are much more spread out as we go down the page. Okay, so they're very different distributions, and we'll analyze what the metric gives us for each of them as our first example. Okay, but first, how do we calculate these things? We square things. Okay, so a lot of experimentation has been done to find out that the square is actually pretty good. You want to deal in absolute distance from how far from the center you are, but it turns out the absolute value function, it works well for some things, but not for a lot of things, so they scrapped that and went for squares. Okay, so they square the distance and add them all up. Okay, so that is known as variance, or the second moment. We talked about expected value being the first moment. Okay, so we just multiplied by a linear term. Okay, so here we're basically multiplying by a square term. Okay, there are 2 definitions well, it's the same definition. I guess this one uses a placeholder mu. If you've never seen a mu before, that's cool. It's all Greek to me too. Okay, so this is the Greek letter mu. Okay, mu. Okay, and it's standard fare. If you read enough of our references, you're going to trip over mu, as they're used that as a placeholder for expected value or average. And a lot of you have seen standard deviation in perhaps a high school course that did some intro statistics, and you've computed standard deviation. They usually use sigma, little sigma, not big sigma, little sigma. Variance is essentially sigma squared. Okay, so that's why I'm using this, but we're going to use VAR primarily. Anyway, what do? You take the expected value of every value that's in the range of x, taken from its mean, and you square those distances and add them all up and take a weighted average of those. Okay, so written another way, it's like this. Okay, using the summation version of this definition, right? So this here is this mu here. Okay, so it got subbed in, and then we expanded throughout that. Okay, so you take the squares of the distances from each. Okay, let's compute the variance of each of x, y, and z from the previous slide. Okay, so the variance of x, okay, is all x in the range of x, where it's x minus mu squared times the probability that x equals x. And there's only one thing in this distribution, right? There's only one thing, and it's 0. So we take 0 minus 0 and we square it. That's pretty easy to do. We multiply by its probability. Multiplying by 0 or 1, those are my two favorite numbers anyway. Variance is 0. Okay, no variance for, it has only, one outcome, right? It doesn't vary. It sort of makes sense, right? It doesn't vary. Okay, variance of y will be non-zero. That's equal to, well, the same thing. I don't want to write that again. Okay, so we'll do the same computation here. We're trying two different things. Okay, so one of them is a half minus 0 all squared times a half. And the other is minus a half minus 0 all squared times a half. Oh, wait a sec, sorry, did I get this wrong? Oh, sorry, it's plus or minus 1. My bad, sorry. This should be 1, and this should be minus 1. Pardon me. I had another version of this in my head. That's my excuse anyway. Okay, so it's 1 squared, or minus 1 squared, times a half. So that's a half plus a half, which is 1. Okay, variance of z is going to look the same, except the numbers here will be 1,000. Or minus 1,000. And 1,000 squared is 1,000,000. So you have 500,000 here, 500,000 here. Okay, so 10 to the 6th times a half, 10 to the 6th times a half, and that's equal to 10 to the 6th. Okay, so no spread for the one that's always the same. That makes sense. It doesn't vary. Variance is in the word. Some small spread for plus or minus 1. Huge variance for plus or minus 1,000. Okay, 3 different, very different distributions. Yeah. Do you still write sigma squared? I mean, I prefer that you use variance, VAR, but anyway. Yeah. Can I go to the last slide? Sorry, do you have another question? How we got to the... Yeah, so these are, where did PR x equals x come from? I mean, that's the definition. Maybe that's the short explanation for this. But you're weighting all of the squared differences by the probability. Okay? So here, like we look at variance of y, the average is 0, and we say 1 minus 0, and we square it, and then we multiply by its probability. So we weight it by its probability. Okay, so we have 1 squared, we have minus 1 squared, and then each of those is weighted by a half. Yeah? Correct, yeah. The random variable only takes plus or minus 1,000 for z. It takes only plus or minus 1 for y. Yeah, it's an exhaustive calculation. We're not, yeah. Maybe that's the point of confusion. I don't know. Yeah. Good. Thanks for the questions. Yeah. Okay. So sometimes big, sometimes small. It all depends. And the more complex our distribution is, we'll see, varying widths. Okay, so let's do Bernoulli. Okay, so Bernoulli distribution, remember, takes, again, 2 values. Instead of plus or minus 1 or plus or minus 1,000, it's 0 or 1. Now, the expected value is p. Okay, so we're going to subtract off from the mean from p each time. Okay, so let's do this. It's going to be a little bit more complicated than the last one, but not by much. Okay, so the variance. Okay, so x in the range is 0, 1, so that's not very much to write, so I'll just write those there. And it is x minus its mean squared times the probability that r is equal to x. Okay, so this bit is going in for this mu, it's p. And we're going to sub in 2 different possibilities. One is 0, and the other one is 1. Okay, so let's give that a whirl. Let's start with 1 first, because, I like to be positive. Okay, so 1 minus p. Okay, so probability p, it's going to be a 1. Okay, maybe I'll just put a 1 in there. And with probability 1 minus p, it's going to be a 0. Okay, and the rest of this is algebra. Let's do it. Okay, so I'm just going to get rid of some of the brackets and stuff. So 1 minus p all squared times p. Just leave that alone. This is minus p all squared because the 0 goes away. So I'll just rewrite that as p squared, 1 minus p. And whenever I'm faced with something that looks like this, it looks, like there's a lot of common factors, right? Right, there's a p we can take out, and there's a 1 minus p we can take out. Okay, so we'll take those out. Maybe we'll do that. And then what's left? We have a 1 minus p from the first bracket, and we have a p from the second bracket. And it's time for big red. Ooh. Yeah, so that's kind of nice. This minus p and this p cancel each other out. And we're left with p times 1 minus p. So the variance is the product of its probability of occurring versus its probability of not occurring. Yeah. Is there an intuitive way of understanding variance? Variance? Okay, so intuitively, like, variance represents how wide the distribution is if you plotted it. Okay, so how it's a measure of how much it varies, right? So how spread out things are. Okay, so is there a way of intuitively looking at a number that's, 1, as in the first example, or a million, as in the first example, that one is better than the other, or one is more varied than the other? I mean, a lot of it, a lot of it depends on the scope of size. I guess we'll see this later, but it's going to take a few weeks. Like the number of times that you sample will affect this number, and it will make it, I guess, less relevant the bigger this number becomes. Here we've taken 2 samples in each case, so 1 million is a huge number in that context. But I think it's all very context specific, so I don't really have an answer. Yeah. Yes. Yeah. So given a variance, can you tell what the probability of the number landing within that variance is? Yes. And we have some theorems coming up for. Yeah. Yeah. It depends on the variance. Yeah.
There's only 2 possibilities, right? It's either equal to negative 1,000 or it's equal to 1,000.
That's right.
Then how is it possible that the variance is a million? It's possible. It's either one or the other. It can't be as big as we. It can't be anything beyond.
Yeah, so how can it be possible that this number is so big, because the number doesn't seem to vary very much? Well, the difference between them is huge. I know there's only 2 possibilities. It's either 50 one way or 50 the other. But yeah, the difference between them is huge. We have an example coming. Okay, I'm not prepared to do it today. Okay, but we have an example coming in about a week, and I promise we'll talk about it in these terms. Why the big spread is so relevant in this case. For something even more relevant, and it's always going to be about money, okay? Because money is really important to me, and it's probably important to you, and we'll talk about this in terms of variance, in terms of risking your money, and we'll see how you feel at that point, okay? So just hold that thought. Okay, well, I appreciate the questions, all of them, but don't have enough time to do the next thing, so I'll take one last question and then we'll call it a day. I don't have time to do the next thing, so just ask me. Sorry, is this linear? Is variance also linear? No. So there's going to be a theorem later. We'll get there. We'll get there, yeah. Is linearity applied to variance? No, it does not. Okay, Wednesday. Shh, sit. Okay, so Wednesday, I will take a little bit of time to your benefit to answer questions, just technical questions about how the midterm's going to go on Friday. Okay, so if you have